Hello friends, here in this video we will see the expression for efficiency of dual cycle. That is, we are going to derive the formula for efficiency of dual cycle. So this is expression for efficiency of dual cycle. Now again, when we are doing the efficiency of dual cycle, for that purpose we require the PV and TS diagram for dual cycle. So I'll start with that itself. So this is PV, that is pressure volume diagram, and TS, that is temperature entropy diagram. So now in case of dual cycle, the first process is reversible adiabatic or isentropic compression. So now this process 1 to 2 indicates isentropic compression, wherein we can see that at point number 1 the volume is V1, that is the volume is greater. At point number 2 the volume is less, it is decreased, so this is V2. So when the reduction of volume takes place and there is rise of pressure from P1 to P2, now this will be called as isentropic compression process. Next, process 2 to 3 is constant volume heat addition. So from 2 to 3 the heat will be added at constant volume, and we can see that there is rise in pressure during the heat addition process, but the volume is constant, so V2 is equal to V3. Then process 3 to 4 is constant pressure heat addition. So when the heat is added at constant pressure, here P3 is equal to P4. Then after constant volume and constant pressure heat addition, there is isentropic or reversible adiabatic expansion, as same as compression, there will be expansion. So process 4 to 5 indicates the isentropic expansion process, and it starts after the fuel addition. So fuel has been added from point 2 to 3, then 3 to 4, and then expansion starts. Next, process 5 to 1 is constant volume heat rejection. So here we see that volume at point 1 and point number 5, they are same. Similarly, I'll show the processes on TS diagram. First is isentropic compression. So during the compression process, pressure rises as well as temperature rises. So from 1 to 2, it is isentropic expansion, entropy remains constant, that is S1 is equal to S2. Then during process 2 to 3 there is constant volume heat addition. So first I'll draw a constant volume line, V is equal to C, and heat will be added on this constant volume line from point 2 to point 3, increasing the temperature and entropy. We arrive at point 3. Then 3 to 4 is constant pressure heat addition. So after constant volume heat addition there is constant pressure heat addition, and now this is very important that the constant pressure lines are less inclined than the constant volume lines. I have shown the constant volume line, so constant pressure line will be less inclined as compared to the constant volume line. As we can see about the inclination of constant pressure line is less, inclination of constant volume line is more. So now After constant volume heat addition, next heat will be added at constant pressure, that is I will move from 3 to on the constant pressure line. So here process 3 to 4 is constant pressure heat addition. So after constant volume heat addition, after constant pressure heat addition, next 4 to 5 is again isentropic expansion. So isentropic expansion, I'll show it with a vertical line, and during the isentropic expansion process, entropy remains constant, that is S4 is equal to S5, but there is drop in temperature. Then process 5 to 1 is constant volume heat rejection. So again I have to move through a constant volume line, which I am drawing joining point 1 and point 5, constant volume line, and here the heat will be rejected from point 5 to 1. So this is the PV and TS diagram for the dual cycle. Now I'll mark here, since 1 to 2 is compression, so this is the work input we are giving in compression process. 2 to 3 is constant volume heat addition, so here I'll write down that it is QA1, that is the first heat addition. The next heat addition is at constant pressure, so this will be QA2. So heat addition at constant volume, heat addition at constant pressure. Next from 4 to 5 we are getting work output, and it is the expansion process, so we are getting the work during expansion. Then 5 to 1, it is the heat rejection process, so that is QR, and it is at constant volume. Similarly here I'll mark the work we are doing in case of compression. From 2 to 3 the heat is added at constant volume, so it is QA1. Next from 3 to 4 the heat is added at constant pressure, so it is QA2. 4 to 5 it is the expansion we are getting, or work which is there in expansion process, so W suffix C. Next 5 to 1 is constant volume heat rejection, so it is QR. Now once I have denoted all the processes on PV and TS diagram, now we can start with the derivation part, and for that purpose the first thing is I'll say that let mass of air m be equal to 1 kg. Here this is the assumption, since we are deriving all the cycles, they are called as air standard cycles, and for that air is the working fluid, which is the assumption, and here I'll take the mass of the gas or mass of the air as 1 kg, and it will remain constant throughout. Next, in the derivation part, first we are going to start with the heat addition process at constant volume, so I'll write down heat addition at constant volume is given by the heat addition at constant volume, we are denoting it as QA1, and that is equal to MCV. It is added from point 2 to 3, so it will be T3 minus T2. Now here, since I have taken the mass as 1 kg, so therefore QA1 will be equal to CV into T3 minus T2. I will keep this as equation number 1. Next, I'll say that in case of dual cycle, the heat is added at constant volume as well as constant pressure. So after constant volume heat addition, now constant pressure heat addition. So heat addition at constant pressure is given by, that is QA2 is equal to MCP. It is added from 3 to 4, so it will be T4 minus T3. So now here I have written the second heat addition, that is at constant pressure, and it is given by MCP T4 minus T3. So therefore QA2 mass, as we have assumed it to be 1 kg, so this will become CP T4 minus T3 I'll keep this as the second equation. Next, therefore I'll write down total heat addition. After this, total heat addition is given by Q is equal to QA1 plus QA2. So I'll simply add the values. So therefore now Q is equal to QA1 was CV T3 minus T2 plus QA2 was CP T4 minus T3, and now since this is the total heat addition, I'll denote it as Q suffix A. So this is QA value. I will be keeping this as equation number 3. Now, as I have written for the heat addition process, similarly I'll write down for the heat rejection process. So therefore heat rejection at constant volume is given by, heat rejection is denoted as Q suffix R, and that is equal to MCV since it is rejected at constant volume and it is rejected from 0.5 to 1, that is T5 minus T1. Here taking the mass as 1 kg as I have assumed, so this will be CV T5 minus T1. Keeping this as equation number 4. Now once I have the heat addition and the heat rejection process, after that we can directly go for the efficiency formula. So here I'll write down that since the efficiency of dual cycle, it is given by, after reaching here I'll write down efficiency of dual cycle is given by, now for that efficiency we can write the general concept that the efficiency of dual cycle will be equal to heat, that is first of all work done upon heat added, or work done is heat added minus heat rejected upon the total heat added. So therefore the efficiency of dual cycle will be, it will be QA upon QA, that will give us 1 minus QR upon QA. So next I am going to put the values. So therefore efficiency of dual cycle will be equal to 1 minus, it is QR upon QA, as we can see here, it is QR upon QA, and QR value we have in equation 4, QA is there in equation 3. So I'll put the values, CV T5 minus T1 divided by CV T3 minus T2 plus CP T4 minus T3. So once I have written QR and QA, I'll say that refer equation number 3 and 4. Next, as we can see from the numerator here and the denominator, I'll take CV common. So therefore, I will get this as efficiency of dual cycle is equal to 1 minus, here we have CV into bracket T5 minus T1. If I take CV common, so here I will have T3 minus T2 plus now CP, it will be upon CV because I have taken CV common into T4 minus T3. So from the numerator and denominator, CV will get cancelled out. Therefore, efficiency of dual cycle will be equal to 1 minus, in the numerator we have T5 minus T1, in the denominator we have T3 minus T2. Now plus Cp upon Cv is called as gamma, that is the adiabatic index, into T4 minus T3. Now this equation I will keep it as equation number A. Equation A. And here now the next hint in this derivation is we have to keep all the temperatures in the form of T3. That is T3 I will keep it as it is, but bring all the remaining temperatures, that is T1, T2, T4 and T5 in the form of T3, and then I am going to put all the values in equation 1. So starting with process 1 to 2, I will say that since for process 1 to 2, which is reversible adiabatic, also called as isentropic process, and for this I'll write down T2 upon T1 is equal to V1 upon V2 raised to gamma minus 1, and it can also be equal to P2 by P1 raised to gamma minus 1 upon gamma. Now we are interested only in the temperature and volume relation, so I'll use only this much part of the equation. So therefore T2 by T1 is equal to V1 by V2, it is called as compression ratio, denoted as R suffix C raised to gamma minus 1, into the bracket I'll write down, since RC is called as compression ratio and it is equal to V1 by V2, that is volume before compression to the volume after compression, also called as cylinder volume upon clearance volume. So therefore here T2 will be equal to T1 into RC raised to gamma minus 1. I am going to keep this as equation number 5th. Next, after going for process 1 to 2, then I will go for process 2 to 3, which is the constant volume heat addition process. So I'll write down now for process 2 to 3, which is constant volume heat addition For that I will write it as, for states 2 and 3 it can be written as P2V2 upon T2 is equal to P3V3 upon T3, and since the volume is constant, so V2 is equal to V3. So from both the sides V2 V3 will get cancelled out. Here I'll write down, since V2 is equal to V3. So now here for process 2 to 3, as we see, it is constant volume heat addition from point 2 to 3. So V2 is equal to V3, so I have cancelled out V2 is equal to V3. Now I'll bring T3 on one side. So T3 upon T2 will be equal to P3 upon P2. Next, I'll define the term P3 by P2 as let P3 upon P2 be called as pressure ratio and denoted by beta. So here what I'll do is T3 by T2 I'll make it equal to beta. So therefore T3 upon T2 is equal to beta, and hence I will get T2 as T3 upon beta. And next I'll keep this as equation number 6. Then after reaching at this stage, here I have got the value of T2 as T3 upon beta, and as I have explained that in case of dual cycle we have to bring all the temperatures in the form of T3. Now T2 is there in the form of T3. I'll put the value of T2 in equation number 5 and get T1 in the form of T3. So after this I'll say that therefore put T2 is equal to T3 upon beta in equation number 5. Here we have T2, so I'll replace it with T3 upon beta. On the right hand side we have T1 into RC raised to gamma minus 1. So T1 into RC raised to gamma minus 1. Next, after reaching here, I want T1 in the form of T3, so I'll shift RC raised to gamma minus 1 in the denominator. So T1 will be equal to, it will be T3 upon beta, and it will be 1 upon, that is into 1 upon, we can say, RC raised to gamma minus 1. So here I'll keep this equation as equation number, it will be equation number 6 for us, that is we have reached up to the 5th equation, and now this will be equation number 6. So we have got T1 in the form of T3, here we have T2 in the form of T3, or what I'll do, I'll keep this T2, this I'll keep it as equation 6, and here I will keep this as equation number 7, making this as 7. So now T2 and T1, they are there in the form of T3. The next thing would be to bring T4 and T5 in the form of T3. So after reaching this, here I'll say that for process 3 to 4, that is constant pressure heat addition, I'll use the concept for the constant pressure heat addition. So I'll write down that since for process 3 to 4, that is constant pressure heat addition, here I'll write down the state equation as P3V3 upon T3 is equal to P4V4 upon T4. And since the heat addition process is at constant pressure, as we can see from the PV diagram, P3 is equal to P4. So P3 and P4 are same, they will get cancelled out from both the sides, since P3 is equal to P4. So therefore here I'll shift T4 on one side, so T4 will be shifted here and this will be equal to V4 upon V3, and T3 will be multiplied here. Next, after reaching this stage, as we can see that the ratio of the volume at point number 4, at point 4 the fuel is cut off, so this is fuel cut off. So the ratio of the point at which the fuel is cut off and the point at which the fuel injection starts. So fuel injection starts at point 2, or we can say point 3, both are same. So V4 upon V2 or V4 upon V3 would be called as the fuel cut off ratio, and it will be denoted by rho. So therefore T4 is equal to rho into T3, and here I'll say that since rho is equal to fuel cut off ratio and it is equal to V4 upon V3, or it can be also written as V4 upon V2 because V2 is equal to V3. Now here I am getting T4 in the form of T3, and as I have explained, we have to get all the temperatures in the form of T3. This will become equation number 8 for us. Next, after reaching here, that is process 3 to 4, I'll go on for process 4 to 5. For process 4 to 5, which is reversible adiabatic expansion. Now for this reversible adiabatic expansion process, we can use the relation that T4 upon T5 is equal to V5 upon V4 raised to gamma minus 1, also equal to P4 upon P5 raised to gamma minus 1 upon gamma. Here we are interested in the ratio or the relation between temperature and volume, so we will utilize only this much part. So next, therefore here in this case I'll use some form of simplification, like V5 is equal to V1, so I'll replace V5 with V1. So therefore T4 upon T5 will become V1 upon V4, it is raised to gamma minus 1. Next, I am going to multiply the numerator with V2 and then divide, so I'll get multiplication and division by V2. I'll write it in this form, that is multiplying and dividing by V2, and if V2 get cancelled, we are going to get the same term. Here there is V4. So now therefore T4 upon T5 is equal to, now V1 upon V2, it is called as compression ratio denoted by RC. Next, V2 and V4. After this, here V2 volume at point number 2 is same as volume at point number 3. So next we can replace V2 with V3, and here it is raised to gamma minus 1. Next, as we have seen previously that V4 upon V3, it was called as fuel cutoff ratio, and if it is V3 upon V4, then it is 1 upon rho, that is fuel cutoff ratio. So here rho will go into the denominator, that is it will be RC upon rho raised to gamma minus 1. Here I will write down, since 1 upon rho is equal to V3 by V4. Next, after reaching up till this stage, the next thing would be, here we have RC and here we have rho. Next, I will be keeping this in such a way that I'll bring T5 on one side. This entire term I'll shift it in the denominator, and in the numerator I'll have T4. So T4 upon RC raised to gamma minus 1, and this rho raised to gamma minus 1 will come into the numerator. Next, T4, we know that T4 is equal to rho into T3 from equation 8. So it is rho into T3 into rho raised to gamma minus 1 upon RC raised to gamma minus 1. I'll say that refer equation number 8. So now here I even have T5 in the form of T3, that is I'll write down, therefore T5 is equal to rho T3 into rho raised to gamma minus 1, I'll keep it as it is, upon RC raised to gamma minus 1. And this I will keep it as equation number 9. So we have all the temperatures in the form of T3, and that we can safely put in equation number A. Now in equation A, we have efficiency of dual cycle. I'll write down, therefore put all the temperatures, that is T1, T2, T4 and T5 in equation number A. So we have efficiency of dual cycle will be equal to 1 minus, now the first term we have in equation A, it is T5, and T5 value is, we have got it in equation number 9, it is here. So I'll put this value, rho into T3 into rho raised to gamma minus 1 upon RC raised to gamma minus 1. This is T5 minus T1, it is there, it is T5 minus T1, so minus, now T1 we have it in equation number 7, that is T1 is T3 upon beta RC raised to gamma minus 1. So it is T3 upon beta into RC raised to gamma minus 1. This is the numerator of equation number A. Then in the denominator we have T3 minus T2. So in the denominator we have T3 minus T2, we have it in equation 6. T2 was T3 upon beta, then minus, here we have plus gamma into T4 minus T3. So I'll put the value of T4, and T4 was rho into T3 minus T3. So as I have explained at the start, I am keeping all the temperatures in the form of T3, and that is the hint. If we are solving the derivation for dual cycle, efficiency of dual cycle, in that we have to keep all the temperatures in the form of T3. Now I can take T3 common from the numerator, T3 common from the denominator. So T3 will get cancelled out, and on simplification I'll get this as efficiency of dual cycle, that will be equal to 1 minus, now in the numerator I have Rc raised to gamma minus 1 common, so that will be 1 upon Rc raised to gamma minus 1 into the bracket. Now here we have rho which is raised to the power 1, so rho raised to the power 1 into rho raised to the power gamma minus 1, so that becomes rho 1 plus gamma minus 1, plus 1 minus 1 gets cancelled out, so it is rho raised to gamma. So in the numerator I have rho raised to gamma minus T3 I have already taken common at the start and cancelled it out, so it is cancelled. So 1 upon beta is what remains here, because we have taken Rc raised to gamma minus 1 also outside. Next, in the denominator T3 has been taken outside, so here we have 1 minus 1 upon beta plus gamma, and it is rho minus 1 because we have taken T3 common. So next, here we are getting the equation which we can say that from this we will get the efficiency of the dual cycle, and it can be simplified and written as efficiency of dual cycle will be equal to, I'll write down 1 minus 1 upon Rc raised to gamma minus 1. Now only this term is the efficiency of Otto cycle, so I am denoting it as, to remember the formula, that this is the Otto cycle. Next, here beta will be getting multiplied, so beta into rho raised to gamma minus 1. In the denominator also here I will have beta, and so finally that will be, here we will be having beta minus 1 upon beta plus gamma into rho minus 1, here also beta was there in the denominator, upon divided by 1. Now this beta would be multiplied, so therefore efficiency of dual cycle will be equal to 1 minus 1 upon Rc raised to gamma minus 1. Next thing is, in the numerator we have beta into rho raised to gamma minus 1, so beta into rho raised to gamma minus 1 divided by beta, and here this beta minus 1 will be multiplied by 1, so that becomes beta minus 1 plus beta into gamma into rho minus 1, that is I am cross multiplying, divided by beta. So here beta and beta will get cancelled out, and finally the efficiency formula will be 1 minus 1 upon Rc raised to gamma minus 1 into bracket beta into rho raised to gamma minus 1 upon beta minus 1 plus beta into gamma into rho minus 1. This I will call it as equation number B. So therefore from equation number B, efficiency of dual cycle can be calculated, and we see that the efficiency of dual cycle, in this we have Rc called as compression ratio, beta called as pressure ratio, and rho called as fuel cutoff ratio. So it depends on these terms, along with gamma, which is called as adiabatic index. So in this video we have seen how to derive the expression for efficiency of dual cycle.